a separate small group and extended time will be continued the next day in class.
Welcome, everyone. It is 4 o'clock, and we're going to go ahead and start.
Why did you start at 4?
I'd like to welcome everyone to today's webinar. We are excited you have chosen to join us today. My name is Janelle Mills, and I am the High School Education Associate in the Office of Assessment and Standards. And my co-pilot today is Lorraine Jackman, and she is our Secondary Education Associate in the Office of Assessment and Standards. By attending this webinar today to the end, you will be eligible to receive 1 hour of credit renewal points. Please make sure to fill out all the forms at the end to receive your credit.
Hi.
I'd like to welcome everyone again and thank you so much for you do every day for the students here in South Carolina. As a disclaimer on the use of artificial intelligence, the content presented is the intellectual property of the South Carolina Department of Education. By participating in this event, attendees agree they will not record, capture, or share its contents without permission. Attendees agree they will not use artificial intelligence to capture or summarize the contents of the event. The SCDE reserves the right to remove attendees using these services. Our purpose today. So today we're going to demonstrate proving theorems without using a formal two-column proof. Proofs. So we're going to be talking about today. Now, I know there's been some questions and concerns, and when we wrap up at the end, I'll address some of those. But right now, we're going to get into what is a proof. So let's talk about what a proof is or isn't. Now, this is the formal definition of a mathematical proof. A proof is a logical argument that demonstrates the truth of a mathematical statement beyond any doubt. It's a step-by-step explanation using previously established facts, definitions, axioms, which are basic assumptions, and rules of inference. Key features of a proof. So the key features of a proof that students should be able to, you ought to be able to see in a proof are logical structure. And a logical structure is every step follows logically from the previous one. Then we have rigor. It, it must be precise and leave no room for vagueness. Universality. Once proven, a statement is considered true for all cases within its domain. And last but not least, foundation based. Proofs build on accepted truths like axioms, definitions, and previously proven theorems. We are only dealing with already proven theorems. So we are not expecting students to know conjectures. We're not expecting them to do formal two-column proofs. And I do understand that you're required to use your HQIM. And I know that at least in one of the uh, HQIMs that formal proofs are addressed in Chapter 1. Students should not be expected to understand proofs or be able to do proofs that early in the school year because they haven't learned enough math yet to be able to have even attempted these two column proofs. Proof should be something that's going on throughout the entire year. It's not just a chapter or a section, and that's why those formal two-column proofs are not what we're looking for students to be able to complete, to do. Now, there are 5 different types of proofs. Well, there's more than 5, but we're going to look at 5 types of proofs. We're looking at direct proofs, visual proofs, indirect proofs, proof by contrapositive, and proof by induction. So when we're talking about direct proofs, a direct proof starts from known facts and uses logical steps to arrive at a conclusion. These include like your flowchart proofs, algebraic proofs, and your two-column proofs. Indirect proofs, your proof by contradiction, they assume the opposite of what you want to prove and shows that this leads to a contradiction. And this includes your coordinate proofs and your paragraph proofs. Then you have your visual proofs. Visual proofs are your proofs without words. They demonstrations use diagrams or illustrations to convey the validity of a statement without text attached to it. They can illustrate identities or theorems, making them evident through visual representation. You have proof by contrapositive. This proves that if the conclusion is false, then the hypothesis must also be false. And we have proof by induction. It is used to prove statements about integers, showing it's true for a base case, and then proving it holds for the next case, assuming it holds for the previous one. So we are going to focus on some direct and indirect proofs and visual. We have a visual proof also. But at no point in time does this statement require the use of two-column type proofs. So let's look at 2025 geometry with statistics indicators using proofs. We have MGSR 5.1, which asks students to justify and apply the attributes of angle relationships, lines, in mathematical and real-world situations. We have MGSR 5.3, which asks students to apply the attributes of quadrilaterals, including diagonals, sides, and angles to prove that a given quadrilateral is a parallelogram in mathematical and real-world situations. And we have MGSR 6.1 to discover and apply the converse of the Pythagorean theorem. Now here's a question, and you can take yourself off mute or put your answer in the chat. Should proofs be utilized in only these indicators?
No, we also use proofs on triangle congruence. There are quite a few other indicators where we can use proofs.
Yes, yes. That brought up the next question. Could this also be applied to MGSR 5.2? And yes, you addressed that. There really are many different indicators throughout the 2025 Geometry with Statistics standards where proofs can be utilized in different ways. And hopefully you can see some of those today in this presentation.
And in the chat, we have Michelle Strickland who said that it can be used throughout the entire course.
Yes, it can. And they should be used throughout the entire course. And that's why formal two-column proofs, again, I stress, do not need to be taught, and they do not need to be, I understand that this year has already started and chapter 1, some people have already covered chapter 1, but going forward, it's okay if you don't do those particular lessons in your HQIM because you're going to be teaching proofs throughout the entire course. And again, it's no need to stress yourself or those students out. when school's getting started, we're trying to build student confidence and their mathematical knowledge. And that's going to come up, that's going to be throughout the entire course.
Okay, and Laurel Hickman said, no, I would expect students to justify their answers throughout geometry. And Praveen said, I've used 2-column and paragraph proofs whenever needed. And Amir said, wherever evidence or justification is necessary.
Yes, and those are all correct. All right, let's look at this first example of a direct proof. Now, our indicator insight asks us to apply in mathematical and real-world context at any point on the perpendicular bisector of a line segment is equidistant from the endpoints of the segment. So they already give us some information. We know that line segment PA is equal to PB. And we see that we have a bisector point P, well, line L. So what do you think would be our next step in this? And remember, we want students to give us some logical explanations. So you can take yourself off mute or you can put your answer in the chat. So we're going to let M be the midpoint of that segment so that AM is equal to MB. What would be could be a next logical statement for this? I have great wait time. We have MP is equal to MP. Okay, good. About a reflexive property. All right.
If that point's on the
Ah,
perpendicular bisector, wouldn't you know that it's perpendicular, forms a right angle,
yes.
and so forth?
So you could do that also. Triangle APB is an isosceles triangle, right? Because we know those two sides are equal. Right. Ah, that's a great idea. Use patty paper to reflect over PM. We have angle PMA and angle PMB are right angles. Great. We know that line L is the perpendicular bisector of AB by definition because it passes through point M and is perpendicular to AB. Ah, we have a side triangle congruence and side angle side. Okay. Let's see what's another step we could have in this. We have let P lies, point P lies on line L. So triangle PAM and triangle PBM share side PM, therefore PM is equal to PM. Good, we had that already in one of our suggested responses. We have angle AMP is equal to angle BMP, which is equal to 90 degrees. Good, we had that as a suggested response. And we have side angle side congruence theorem. Triangle PAM is congruent to triangle PBM. Now let me ask you this. So you all had these responses and they were in different orders, but did we come to the same conclusion? Yes, we came to the same conclusion. So in your classroom, would you have marked your students wrong if they used any of this but came to the conclusion that the two triangles were congruent?
No, as long as they have rational thought, there are multiple ways to end up with the proof of the two triangles being congruent. Sometimes you go a little bit longer, sometimes you know a different shortcut. There are multiple different ways of proving the triangles are congruent.
Right. Yeah, we were trying to show that PA is equal to PB. So we wouldn't necessarily need to use the side angle side. But this also could be used for MGSR 5.2 because that is where you are proving that you need side angle side. They actually and I'm not looking at it exactly right now, but that talks about your triangle congruence and your similarity. Are students able to demonstrate if they had any of these points? Is that a way for them to demonstrate their knowledge? Or should I say, what is the goal of students learning proofs?
Logical thinking and following step by step to get from point A to point B. So, but basically just logical thinking and logical reasoning.
Yes, we want students to be able to have those logical thoughts, logical reasoning. We want them to get used to justifying their actions, justifying their decisions, justifying their thought process. Now, when students start justifying and having these conversations in class, whether you're doing this together as a class, whether they're working together in pairs or groups, what is this conversation and this discourse helping you as a teacher? How is it helping you as a teacher?
To see what they know regarding our content. So, if they didn't know perpendicular bisectors make right angles, we can hear that if they don't mention that, maybe they need to be reminded of that. So it gives us ideas of what we need to reteach, what we need to remind, maybe have anchor charts of with our theorems that they're forgetting about sometimes.
Yes, that is what we want students to be able to do. They do it all the time in English. They have what they call brain dumps, right? We want to know what students know because sometimes when you ask a student, well, where are you confused? They'll say, well, I don't understand anything. Like, I don't understand any of it. But they do. And they do have more math knowledge than they give themselves credit for. And sometimes it's just a matter of the confidence or letting them be able to tell you, well, what do you know? And it's okay to ask them, okay, let's look at this figure. What do we know looking at this figure? What is given to us already? What are we trying to find? Oh, I didn't get to the last bullet. So because the triangles are congruent, their corresponding parts are equal, which means that PA is equal to PB, and any point on P is equidistant from the endpoints of the segment. As long as the students get to their logical reasoning. We could talk about order later. We can help them because maybe their order is off. Some students, they might begin with the end. They might see the beginning, see the end, and then they need to fill in the middle. And that's okay. We don't want to dictate how students think because we want them to think a lot of times outside the box. And we ask them to think outside the box a lot, and then we want to penalize them when they don't think like our answer key might tell them they're supposed to think. I don't care what the answer key says. Proofs is one thing where you're going to have to read it. You're going to have to see if it follows a logical thought. If it doesn't, maybe have a conversation with that student about what they were thinking when they were writing their paragraph or putting their bullets down or drawing a flow chart. And it's okay to give them options of doing proofs in different ways in their class. Show them different ways and see what they're more comfortable with. Because it shouldn't be, oh, you have to do it like this or it's just not going to be correct. Because if you have a class of students that's failing, well, that's probably why. All right, let's look at this. This is an example of an indirect proof, a coordinate proof. So we have a coordinate and we have some given points. We have point A which is at 1, 2, point B at 5, 2, point C at 6, 5, and point D at 2, 5. So what type of figure are we looking at?
Parallelogram.
Parallelogram. What else could it be called?
Quadrilateral.
Quadrilateral. These are questions you should be asking your students. Give them a coordinate, a geometry, a coordinate grid, a figure, a quadrilateral, and a coordinate grid. And then you ask them, what do you notice? What do you see? Now, if you're in a class and you have this on paper, what would be the next question you might want to ask students?
How do we know it's a parallelogram? How do we know it's a quadrilateral?
Exactly. How do we know it's a parallelogram? How do we know it's quadrilateral? What are some other things you can ask students to find out about this figure just before we even start talking about a proof?
There's some answers in the chat. Can you verify it is a parallelogram? The lengths of the sides? Does the diagonals bisect each other?
Let's stop right there. Length of the sides. That's great. What could we have students actually do? Is it a rhombus? Okay. So let's say you give this to the class, find the distance between the 2 points. They can find the distance between the 2 points. They can do this several ways. Should they be using, we don't necessarily want them to use the distance formula. How else could they begin to understand the distance formula without formally using it? Okay. We could start with talking about the slopes. So we could start with talking about the slopes. Could students actually measure these using a ruler? Count the distance? Exactly. Have students count the distance. Have them measure the distance. What could we do with the angles?
Draw triangles.
We could draw triangles. Good. They could use a protractor, measure the angles. They could count the number of units. Exactly. So if we were to ask them about points A, D, and B, C, they would, well, I don't know if they normally do it, but a good way to do that would be to use the slope. And then they would see that, of course, line segment DC and line segment AB, they would be able to see that those are the same. They could use the measures. They could use the angle measures. So just this one example, and we haven't started talking about proving anything yet, but students are they're learning about quadrilaterals, they're learning about distance, they are learning about angle measures, they are figuring out if this is definitely a parallelogram. We don't know, it looks like a parallelogram. Well, does it have all the attributes of that parallelogram? Slope to get the concept of opposite and parallel sides. Yes. So does this indicator also address another indicator in standard 5? Is it just 5.3 or could this be another indicator? Yes. because we could talk about the properties of parallel lines. These indicators do not have to be taught in isolation. The book might give it to you in isolated chapters or lessons. This does not have to be taught in isolation because you honestly could cover all three indicators in a few lessons together because they all relate to each other. All right, so let's look further into this one. So we know that the slopes of line segment A, B, and CD equals 0. We've already talked about that. We've had that conversation, so that's a point that we can put down just looking at our points. The slopes of line segment A, D, and B, C are 3. Opposite sides are parallel. We could use the lengths of the sides using the units. And of course, like I said, we can have students use a ruler to measure the other sides. And we found out that opposite sides are equal. Oh. Exactly. And you could have students show the work for each step, yes. So as we look at this, and we've talked about this, and the questions I'm giving you, and I know some of you are like, oh, this isn't what I expected. These are the conversations you should be having with your students in class. It shouldn't be you giving them an example and you telling them, okay, this is what you're looking for. And that's why I say conjectures, we're not worrying about those. We want students to be able to have these discussions, be able to think through something they see. So when they see a figure on a test or an assessment, they don't automatically say, oh, I don't know what this is, or they go straight to the answer or their answer choices. Or if they have an open response and they're not able to, we don't want them to look at it and say, well, I just don't know where to start. We want them to be able to look at an image, disseminate the information, figure out what it is that they know, and then kind of help them put it into a logical order. All right, here's our final one, visual proofs of GS MGR 6.1. So our statement is the converse of the Pythagorean theorem. If a triangle has side lengths a squared plus b squared equals c squared, then the triangle is a right triangle with the right angle opposite the side of length c. So we started with just a drawing of a 3 by 4 by 5. So now there are no words to this proof, simply figures. Now the way I did this was I measured out 3 by 4 by 5 using a ruler in millimeters. Then using an algebra tile, one rod was equal to 5 units. So to prove this, we want to talk about squares. So students should be able to show you that each side is an actual square. The leg that was 3 units is a 3 by 3. How did we demonstrate this? Because it shows that it is a 3 by 3. It's 9 square units. Then we have side 4, which is a 4, 1, 2, 3, 4 by 4, 1, 2, 3, 4, and it makes a square. So that gives us 16. Now, when we talk about the Pythagorean theorem, and sometimes students don't actually understand that concept, they forget that if it's a squared plus b squared equals c squared, then if we add up the square that is a 3 by 3 and the square that is a 4 by 4, we should get a square that is a 5 by 5. which is what we did here. So 5, one of these bars, of course, is 5 units. So that's 5, 10, 15, 20, 25. And when you put it together, then a squared plus b squared can equal c squared. Now, I see in the chat, I know it's a lot, but I think the bars would be confusing. Right, 25 small squares would be easier to demonstrate that. But if you want them to be able to see where one could be equivalent to something else, then this would be a way to do that. But I agree, 25 squares. I personally I didn't have 25 squares to put on here. And I didn't want to move all of those into one space. But that would be a great way of showing it also. We took the different color squares and filled it in where the green bars are. That would be a great way to show them also that that is an equivalent amount to what they see on both of the legs. Now, how could you do this? You give students an example. What could you do to have them demonstrate an example of this for you in class? Use a different triple and grid paper. Yes. Could you have students, what else could you do? I'm going to ask you, what could you do in using the triple and the grid paper? How would you have students demonstrate their understanding of this? Okay, you could give them sets of triples. Should you give them sets of triples, or should you let them find sets of triples? You can take yourself off mute, or you can respond in the chat.
I would let them find them that way, because they're finding them on their own. They're more likely to remember some of the lower triples, like the 3, 4, 5, and such. And also, when I do these, I use straws.
Oh, that's a great idea. Yeah, have them do an investigative activity. Now, should students be doing this individually, or most best best idea is to maybe have them work with in a pair or group?
I usually give them a challenge and try to make it small group work. So since I have tables that are round and such, I have 3 or 4 students at each table, and it's like, okay, we have different lengths of straws already cut. How many right triangles can you make with these sets of straws?
Yes. Great, that's a great idea. What else could you do in a class to show this, or have students demonstrate a visual proof? And it doesn't necessarily have to be this proof, but any visual proof. We have straws, we have algebra tiles. What other instructional strategies could you possibly use? Grid paper, algebra tiles.
One thing I've done with my geometry class is not necessarily to do a proof, but understand how to do a proof, is we've played Uno. And each time they lay down a card, they have to explain their reasoning why they were able to put down that card.
That's a great idea to help with the logic, the thought process, the reasoning. Because that's what we want students to do. Again, we want them to be able to logically reason. And that's why I do understand, and in one of the HQIMs, they have inductive and deductive reasoning as lessons, but that's not explicitly stated in any of our indicators. And so that's not something that needs to be an individual lesson, because as you're going over proofs and you're talking about reasoning, you can introduce those concepts, but they will see that later on in reasoning and mathematics, application and modeling, and statistical modeling. All right, so as we wrap up, or let's recap what we talked about today. So, what's one shift that you can make in your instructional strategies that we've talked about today?
Moving more away from the traditional two-column proofs that have been very central to geometry, and moving towards more like the mapping we've been doing, and the more like the paragraph proofs, offering more options than just doing the two-column.
Great. Yes, that is definitely one shift you can make. What's another? Introducing visual proofs. Great. Anyone else? What's another shift that you can kind of make in your classroom? And if you've already taught proofs, that's fine. But going forward, what could you do differently? Great. Ask more thought-provoking questions about the connections of the different concepts and making proofs. Integrate proofs in all
Making
units.
proofs
Yeah.
more, making proofs more of a discussion.
Yes. Make them more of a discussion. You have the autonomy on how to grade. And I'll say this geometry was not ever intended to be difficult. It's it's not hard. And we want students to be able to have some low floor entrances, some low entrances, and some high ceiling exits. So we want to see growth. I'll stress this, I'm continue to stress this. Honors level does not mean you go on to the next thing or you teach above and beyond where that student needs to go. The idea is to go deeper into a concept. We have another interest. Make the teacher to be the guide on the side and make the students the sage on the stage in discovering concepts in geometry. Yes, it is okay for students to explore and discover this math with some guidance. You may have to guide them in one area or another, but they'll be fine. It's productive struggle. That is one of our process standards. We want students to feel comfortable with math. We want them to get that basic understanding, find out what they know, and allow them to apply it. We have integrating visual proofs and using proofs to elaborate concepts. Exactly. Those are some great comments. I'm kind of scared to ask this question, but how many of you feel a little bit better after going through these examples and having this discussion about proofs? Yes, we want students to foster real mathematical thinking. That is what this is about. So I know we have just a quick visual for me to just see that you were able to, that you feel a little bit more comfortable about proofs. If you're more comfortable after this webinar about proofs, put a 1 in the chat. If you still kind of need some help or some guidance on some things, and put a 2. All right, I see a lot of 1s. Great. This class is not meant to be stressful, and I know the change has been a big change for a lot of educators in South Carolina, but it is not meant to be difficult and it's not meant to be a burden. There are 33 indicators. And a lot of these indicators can be taught together. I understand the HQIM are thick and they come in a lot of, there are 2 and 3 teachers editions to some of them. I just ask that you continue to take it in stride, but I don't want proofs to be a hang up for students, because I've been hearing that, oh, we can't get out of chapter 1 and we can't get out of proofs. There was honestly no expectation for them to be at the beginning of the year, because students don't know enough math to be able to have those type of conversations. They know a good little bit of math by the time they get to 8th grade and 9th grade, but the theorems and the things that we're asking them to prove or to be able to recognize the patterns and make generalizations about, they still have some learning to do. And so that's why these can be introduced and used throughout the course. Oh, great. Geometry with statistics can be either semester course or a year-long course. If it's year-long, then you really have time to explore. So if you're at a school where you're on a year-long for math, you have more than enough time to explore these indicators and these concepts with students. Yeah, even with your 8th grade, your compacted 8th grade with geometry with statistics, there's still enough time, because there are some 8th grade standards that follow right along with our geometry with statistics standards, and they can still be taught together and not in isolation. So it's more like you could build on that 8th grade standard. So students are still getting both indicators without there being a total lapse. Like, they're not different. It's not like you're teaching 8th grade standards and then geometry standards. They can be integrated together. All right, so this is your attendance code and your feedback survey. I ask that you please complete this in its entirety. And at the end, you should get your certificate should be emailed to you directly. If you don't receive a certificate, just let me know and I'll make sure that you receive it. Please check that your email is spelled correctly, because if it's not, then it will bounce back. And be sure to also check your spam folder, because sometimes our stuff gets sent to junk mail. I thank you for attending today, and I hope that you continue to have a great school year.